Howdy.
Howdy. Let's get started. So Matt is going to talk to us about algebraic geometry in the spectral theory of discrete periodic operators. Take it away, Matt.
Awesome. So first, thank you, Jordy, Taylor. I'm so bad with names. I'm sorry. Nick. Yes, talked to you several times, and Luis for organizing this conference. All right, first mistake made already. All right, let's keep going. And thank you all for coming to this talk. I'm going to talk about an application of algebraic geometry that as Frank introduced me to. And yeah, so really I'm going to be talking about problems that are coming from mathematical physics, namely what's referred to as the tight binding model. And I guess one of the main things I'll be using throughout our Newton polytope. It's going to involve somehow this graph here, and we're going to talk about this set of two hypersurfaces over here that gives us a something called the block variety. But I'll define all this in a second. Let me start by introducing. Oh, I have this. Okay, periodic graphs. Okay, we'll use that instead. Is it frozen? Okay, that worked. All right. All right. So ZDPR graph is a simple infinite graph equipped with a CD action that acts on the vertices and edges of our graph. So I have an example here, which I already mentioned, is the hexagonal lattice. It's a Z2 periodic graph. Our Z2 action is represented by these two vectors here. This is the oh. That's how it works. Okay, never mind. I'm not going to use that. I'm just going to point. I don't like that at all. Okay. All right. Okay, so we have this Z2 action. Hopefully, you can see that with respect to this, respect to these translates, we can reach every vertex if we start at one of these two vertices. So we have two vertex orbits in this case. Similarly, if you were to look at the edges, you'll see that there are three edge orbits. Since these two edges are shared, these two edges are the same, and then if you span out those orbits, or sorry, yeah, if you span out those edge orbits, the remaining orbit is just by these here. All right. Anyway, we're going to refer to a representative set of the vertices. For example, this vertex and this vertex. So a representative set of the edge orbits as a fundamental domain. This won't come up too much, but I'm going to use E gamma and V gamma to denote the edges and vertices of gamma, respectively. So, so like as our action is, in this case, we've realized in real space, we're acting on the graph via translation. So if we were to, right, so this is, will this be one orbit over the section? I guess let's pick the okay, wait, what part's confusing? I'm not saying this well, but.
Group acts on the set of vertices with finitely orbits. It acts on the edges with finitely orbits. They're not unrelated. Bounded degree implies the second.
Okay, much better said. All right, thank you, Frank. All right, the main object we want to study is known as a discrete periodic operator. In order to define this, I first need to pair of functions, which are referred to as a label. And it's made up of two ZD periodic functions, one that sends our vertices to real values and one that sends our edges to real values. This first function B is usually referred to as a potential, and E is referred to as an edge weight function or an edge labeling. And just let G denote some function on our vertices. Then a discrete periodic operator is a potential multiplicative operator plus a weighted graph Laplacian. So at vertex U, L sends G to the potential. This is just that multiplicative operator, V of U times G of U. And then this is our weighted Laplacian piece where we're going to sum over all the neighbors of U, and we're going to take the difference of G of U and G of V and scale that difference by the weight assigned to that edge between them. And what spectral theorists who work on these problems with physics are interested in is studying the spectrum of L on the space of square sumable functions on the vertices. So what we're first going to do is make this more approachable by using the Fourier transform, or in this case, it's often called a Fourier transform. Now this might look somewhat intimidating, but Fourier transform is just a operator that's going to send our functions in the space of square sum functions on the vertices to a vector of square integral functions on the d-dimensional torus by just think S1, but now d of them. Right? And the W there is just to show that we have a W many vector of square integral functions on the d-dimensional torus. So, you might, yes? Let's see. In the transform? Yeah, A is a D2. Oh, sorry. Yeah, Z is a vector. So Z is a vector, is a d-dimensional vector that takes values on the d-dimensional torus, right? So S1 cross S1 cross S1 dot 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 d times. Yes. Yeah. Oh.
It's a monomial.
Yes. Yeah. Exactly. So what we're really doing here is just taking a Fourier transform on each vertex orbit. Hence why you can end up getting just a vector representation for our function g of z. And if we were to work this out, it's just a pure calculation exercise in calculation. You can show that if you let L hat be this unitarily equivalent operator that's just given by, so F star is just the inverse Fourier transform. Then we apply L, then we apply the Fourier transform. And we want to apply this to functions in our L2 to the W space. We get the following expansion. So you might notice this is very similar to before. L hat acts on G hat at Z comma U with, we have the multiplication piece. And once again, we have this graph Gaussian piece. The difference is now we can express every vertex as some element in our fundamental domain translated by vector A. And because we have this here, we can pull that out. So now we just have a linear sum in terms of G hat and the values it takes with respect to vertices in our fundamental domain. Now we've reduced this to just studying a finite dimensional vector, and we can view now L hat as acting on these functions just via a finite W by W matrix. W just being, again, our fundamental domain. And the reason we're doing this is we can now recover the spectrum of our original operator L on the space of square sum functions, because these L is unitarily equivalent to L hat, and they're just given by collecting the eigenvalues of L of Z as we vary Z over the d-dimensional torus. And this is fairly dense, so let me just do an example that will hopefully make this easier to absorb. All right, so I'm just writing F hat for some function L2 T2 UV, and we're working with the hexagonal lattice. You might notice I dropped the Z. This was just to, these are still functions on a torus. I'm just not writing the Z, so these would fit. But so L hat is going to act on F of U. So first we have our multiplication piece, so that's that U, V of U there with the F hat of U. Then we can start going through our way of Laplacian. I've assigned to these weights, I guess E is just being the labels alpha, beta, gamma. These just represent those edge weights. And so we can start with this edge. We have the difference of F hat of U minus F hat of V. Then we scale that difference by alpha. So you see alpha F hat of U minus alpha F hat of V. We can go over this edge here. We again take the difference F hat of U minus, but now we have minus AX plus V. This AX gets pulled out as X inverse. So we have F hat of U minus X inverse F hat of V, and we scale that difference by beta. And we just continue in this manner. And the essence is once we now start collecting these coefficients, we get our Fourier matrix, Lx, y. And one thing to notice, and this is why I assumed initially that those functions V and E are real. If we have X and Y restricted to the unit circle, this is self-adjoint. So all of our eigenvalues are real for this matrix here. Hermitian, yes.
Hermitian matrices are self-adjoint operators.
Yes, here's this. Okay. However, we don't necessarily need to, if we want to study, I guess, the operator in display. All right, I'll mention more there. Okay, I don't want to. All right. Okay, so the main object that we want to study, so this is on the tail slide, is the block variety. So the dispersion polynomial is just the characteristic polynomial of our K matrix. And the block variety is the vanishing set of dispersion polynomial. And we'll also briefly mention Fermi variety. So this is just the block variety at a fixed lambda value, but vanishing in now T2. So as mentioned before, this is a Hermitian matrix. This has real spectrum. So we can realize the block variety if we restrict to T2 as living in T2 cross R. I guess some other aspects I'll mention. Notice we have these sheets here. These are the vanishing sets of functions called band functions. The projection gives closed intervals of the spectrum, which are referred to as spectral bands, and these endpoints are often referred to as spectral edges. And of course, we could also consider the block variety in the larger algebraic torus, C star squared cross C. By C star, I just mean very complex numbers, cut 0 out. Since we go back to our matrix, right? This is a matrix with the Laurent polynomial entries, so everything's nice. Our dispersion polynomial is nice and well defined, as long as we are in C star. Right. Okay, so why are we using algebraic geometry to study these objects? I mean, a lot of people work on discrete periodic operators, but many of them are functional analysis. They don't, I guess, go for these tools. So I wanted to briefly describe some previous works that have used algebraic geometry in the study of various problems coming from spectral theory. And the main ones I will talk about today are for studying the spectral edges. So these correspond to, as I mentioned, those endpoints of the spectrum. And I'll also talk about irreducibility of block theory varieties. So these are, again, this is just an algebraic property, but this has consequences for the spectral theorist in terms of certain properties of our spectrum, which I'll mention as we get there. But these aren't the only two types of questions that spectral theorists have that we can use algebraic geometry to solve. We can also discuss locate Fermi spectrality, density of states, bound states / flat bands, existence of spectral gaps, and other types of problems. I won't go into these, but I just want to make it clear that there's more than just these two things, even though what I'll say from here will restrict to these two concepts. Okay, so let's talk a bit about spectral edges. So one of the reasons to study the spectral edges is this well-known conjecture, at least to the spectral theorists, known as the spectral edges conjecture, which states that generically extrema are isolated, not degenerate, and they occur in a single sheet. By generically, I mean for a generic choice of labeling, one expects these properties to hold for the edges of this band. So, and these are with reference to the corresponding extrema of the actual block variety. And this has consequences for the mathematical physicists and relates to effective mass, Anderson localization, and other properties, which I won't go into detail. I just want to get across there are reasons to study this, and these spectral theorists care whether this conjecture is true or not. And it's whenever you want to study extrema, one of your options is to study the larger set of critical points of the block variety. So our critical points are just, right, first we need to, so if we want to study extrema, we need first to actually be on our variety. Then we need a horizontal tangent plane given by P. So indeed, our critical point set will contain all our extrema. And one of the things me and Frank looked at is trying to figure out when we can, when we're in a situation where all critical points are isolated multiplicity 1, since if we know that, we get 1 and 2 immediately. If you want 3, you can always check that yourself, I guess, with whatever model you're dealing with. Okay, so one of the main tools that we use for studying spectral edges, and also these will also come up when I start discussing irreducibility, are Newton polytope of a function. So a Newton polytope is just the Newton polytope of a polynomial is just the convex hull of the exponent vectors of that polynomial. So take any term that shows up in your polynomial, send it to a point in space, so x to the r, y to the s, lambda to t gets sent to rst, and plot those in space, take and take all points in between. Okay. Besides that, we also need to know what a face is. So a face is just a collection of points on a Newton polytope, typically on the boundary, that are simultaneously minimized by some linear functional. For example, we have a face here. If I were to take the dot product of all points on my polytope with -2, -2, -1, this is the collection of points that are minimized by that vector. And I guess the only other thing I need to mention is if we restrict to the monomial terms that show up on that face, this is just referred to as a facial polynomial. And make sure you actually hold on to coefficients coming from your polynomial, don't just sum up the monomials. And moreover, if your face is dimension 1 less than your original polytope, we refer to these as facets. And in the case of the polynomials we're dealing with, we always have a special facet, which is all the points where lambda is 0. We refer to this as the base of the polytope. And you might notice this is a pyramid. These aren't necessarily always pyramids. Anyway, okay, so what Frank and I showed is that so if given just a ZD periodic graph, you have a discrete periodic operator L, and just let phi be your collection of critical points, you have exactly d+1 factorial times the volume of the Newton polytope of your dispersion polynomial, isolated critical points in C star to the d cross C, counted with multiplicity under some conditions on the facial polynomial. So I mean, we've seen this many times at this point. Right? This is just Kucherenko's theorem, but our polynomials are not necessarily generic, so we need to actually. This is us giving conditions under which our polynomials satisfy Kucherenko's theorem. So in particular, we need the vanishing set of our facial polynomials. They should all be smooth at infinity, and we should also have no proper facial polynomial that's vertical. So by vertical, I mean our polynomial should not contain both the terms z to the a and z to the a lambda b for any a and non-zero b. I shouldn't, yeah. So after we found these conditions for when our system of, when our collection of critical points actually satisfies this bound, we want to know if we can actually come up with a family of operators that actually satisfy these assumptions. And in order to talk about those, I need to tell you what a dense periodic graph is. Yeah, of course. Yes. Oh yeah. This is also an upper bound.
And then the part of your theorem is to show that, in fact, all those positions, that number is in fact equality.
Basically, yeah, we want to come up with some examples where we achieve equality.
No, the theorem gives conditions under which it's achieved.
Oh, I see.
There's been a small industry where people have shown that this is like the first one, certain optimization problems, which are not general polynomial systems, achieve the combinatorial bound despite not being general. And there's people in the audience that showed the area.
The theorem that you're applying is generic in what sense?
Okay, Paul Brighting calls this Bernstein general. It says that no facial systems have any solutions. That's what Bernstein's second theorem gives conditions for which the bound is achieved, and one has to show that happens if you don't have general polynomial.
Okay. Yeah, so exactly what brings this is when the bound is actually achieved. In general, number of solutions, if these conditions aren't satisfied, is necessarily less than this. At least the number of isolated solutions. You could always have like a curve or something, but anyway. All right. So we wanted to find a family that such that the for generic labeling, our discrete periodic operator actually has a block variety that satisfies this bound. So the family we look at are dense periodic graphs. So a ZD periodic graph that as many edges as possible given support is referred to as dense. So what do I mean by that? Well, first off, the subgraph induced by the fundamental domain should be a complete graph. Moreover, if our fundamental domain shares any edge, we have a vertex that shares an edge with some shifted copy of our fundamental domain. So for example, if this is our fundamental domain W here, this is W plus 1 comma 0, then we should have all edges possible between W and W plus A. So basically the induced subgraph of W, of the vertices of W and the vertices of W plus A should also give us a complete graph. And one of the reasons to look at this is if you're missing edges, you can always add them. So any periodic graph is contained in a dense periodic graph. So over here, this is the hexagonal lattice we've been looking at, slightly different picture of it. And this is the corresponding dense graph that's contained in. There's technically many dense graphs. You could put this in depending on your choice of fundamental domain. But in this case, if we choose this as our fundamental domain, this is the respective dense graph that contains it. And what Frank and I showed is that if you have a Z2 or Z3 periodic dense graph, then you'll have exactly d plus 1 factorial times the volume of the Newton polytope of our dispersion polynomial, many critical points, for a generic labeling. And this agrees with work of Doe, Kuchman, and Frank. They studied specifically this graph and showed that it has 30 critical points, and were able to prove the spectral edges conjecture for this graph in that paper. But, okay, and I guess I should mention that we have only Z2 or Z3 because necessarily once you go into higher dimensions, this fails. There will always be facets with such that the dispersion polynomial at that facet has singular points. So it's
It'll also have no isolated critical points.
Yes.
No, the singular locus, which is one-dimensional.
Yes, that's correct. Yeah, good point. Yeah. All right. And since a lot of this conference has revolved around using computation to prove things in algebraic geometry, I wanted to mention one of the parts of our papers where we compute the following example, and we're able to, through one computation, we're able to show that at least the spectral edges non-degeneracy conjecture, so just those first two conditions, isolated non-degenerate, is true for 2 to the 19 minus 1 graphs. And this is because the Newton polytope that corresponds to this specific graph is the same as its dense counterpart. And since we were able to find exactly the number of solutions you'd expect for the dense graph for this particular graph for a generic labeling, you're able to extend that to any graph this is contained in between this graph and its dense counterpart. Okay. Apart from talking about the spectral edges conjecture, another project I worked on during my PhD was studying irreducibility of these graphs, and this is based off some joint work with Jordy. Specifically, we want to, so we've been viewing all these graphs as just Z2 periodic and taking that as the only possible model for that graph, but any Z2 periodic graph is also periodic with respect to a sublattice. So we want to know whether, so if we start with a Z2 model and we know that the corresponding dispersion polynomial is irreducible, can we somehow preserve that as we take a larger fundamental domain? So we're now viewing our graph as being periodic with respect to some free fall rank sub group of Z2. Here's an example, right? Again, this is the hexagonal lattice that we've been looking at, and now this is the corresponding graph when instead of viewing it as Z2 periodic, we're viewing it as 3Z by 2Z periodic. So there are some connections between this, but fundamentally, right, this is a characteristic polynomial of degree 2, is a polynomial lambda. This is, here we get a characteristic polynomial of degree 12, and especially for, and what we're specifically going to look at is what happens as we change the period of the potential. So we're going to fix edge weights to be Z2 periodic throughout, and we're going to allow the potential to differ. First, the first thing we looked at, let me see. I used phi sub AB to represent the characteristic polynomial of gamma when we were viewing it as AB is Z periodic. If you just see phi, then we have not modified periodicity. And one of the things that Jerry and I showed is if we just change the fundamental domain, so now we take we're looking at this as 3Z by 2Z periodic, but we still only allow V to take 2 possible values. So our the potential we pick for this model is still a valid potential for the original model. Then we have the following. So if our original polynomial is irreducible, and it has a term of the form x to the r, y to the s, lambda to the t, then as long as A is coprime to both B and R, or B is coprime to both A and S, then irreducibility extends to phi sub AB. Moreover, if you actually know more about your support, then you end up with less restrictions on your choice of periodicity. So for example, if you have both x and y appear as terms of your dispersion polynomial, then it doesn't actually matter what you choose for A and B. You always have that phi sub AB is irreducible. And people might be wondering, why study this in the first place? Well, first off, these types of models have been studied since the 90s through Giesinger, Kroner, and Tribowitz's so the Geometry of Algebraic Fermi Varieties, a book where they study irreducibility and many other aspects of this graph here. This is known as the square lattice. This is viewing it as 3Z by 2Z periodic, but you could also have chosen just a single vertex as your fundamental domain. And there wasn't all that much work done on this until fairly recently, where Winsai Liu generalized their results to higher dimensions. And then after this, there was some work by Philman, Liu, and Matos studying a similar question, where they generalized this to other graphs of this form, where you have just a single vertex orbit with respect to the original action, but you're able to kind of decorate this graph however you want. You can add more edges, and there's some way to then find choices of changing your periodicity where everything's irreducible always. And that's, I guess, sorry, that's something I wanted to emphasize. Right? If we know there's some Z2 periodic potential such that this is irreducible, we're kind of good in the case of is this generically irreducible? But in a lot of these previous works, you can do much better. You can actually show that it's irreducible always. It doesn't actually matter what your choice of potential is. You can always show that after you change this periodicity, irreducibility is preserved. So one of the reasons to actually care about irreducibility for the spectral theorist is Kuchma and Weinberg in 1998 showed that if your Fermi varieties are all reducible, this implies you cannot have any embedded eigenvalues. So the spectrum I showed you before, that's basically almost always a central spectrum. There's no true eigenvalues in the sense of having eigenfunctions in the space of square-ensemble functions. Or I guess this rarely happens. And in the case all your Fermi varieties are irreducible, it doesn't happen. And for a while, I guess, studying irreducibility of just block varieties didn't really have much of an application until recently, when Liu showed that irreducibility of block varieties is a key component for proving quantum ergodicity. So this has to do with the distribution of, I guess if you're thinking of your eigenfunctions as like probability functions, it has to do with the distribution of those probabilities. I won't go too much on that. So what me and Jordy wanted to do was see if we could extend these results to more general graphs. So not just being restricted to your initial fundamental domain only having one vertex. For example, hexagonal lattice, there's no choice of period such that you only get one vertex in your fundamental domain. So that particular model will not be covered by the results. And the way we went about doing this is by studying the connection between these two polynomials as we, again, change the period. So one thing to keep in mind is there's a nice relationship between the Newton polytope of our dispersion polynomial phi and the Newton polytope of phi sub AB. In particular, you can go from this Newton polytope just through a linear map. Just scale the x coordinate by a factor of b, the y coordinate by the points of your y coordinate by a factor of a, and then your lambda coordinate by a factor of the product of a and b. One more thing I need to introduce some background is this concept of Minkowski sums. This is a way we can add together our polytope. In particular, you can just define to be the pointwise sum of the elements of the points in your polytope, and how this is going to help us with irreducibility is it's the fact that the Newton polytope of f summed with the Newton polytope of g under the Minkowski sum is equal to the Newton polytope of the product of f and g. And here's just a little example. Okay, so we say that an integral polytope is only homothetically decomposable if it can only ever be written as a Minkowski sum of two scalar copies of itself. So if it can be written as a Minkowski sum of two smaller integral polytope, they must both be scalar copies of itself. So a example is a pyramid. So take, I guess, your favorite linear hypersurface and take a finite collection of integer points, and then take some point off that sorry, not hypersurface, hyperplane. Take a point off that hyperplane and take the convex hull, and you get a period. The most obvious example is a triangle. So here's took 2 points on some linear plane, or like took 2 points on a line, took a point off the line, took the convex hull. A triangle can only ever be an integral triangle can only ever be written as the sum of two integral similar triangles. So you need to preserve angles or side lengths. And other examples are the polytope we've already seen. Both of these are pyramids. You have it's a pyramid over the base. So what we looked at are polynomials that have a very similar properties. So these are what we call only homothetically reducible polynomials. So we say that a polynomial is only homothetically reducible if whenever it factors, then its factors g, so if f factors into g and h, then the Newton polytope of g and the Newton polytope of h must both be scalar copies of Newton polytope of f. And by scalar copies, we include if you just multiply by 0 if you're just adding, and if you were to write this as like f times 1, for example. So if the Newton polytope of f is only homothetically decomposable, or f is irreducible, then this implies that f is only homothetically reducible. However, the converse is not true. It doesn't necessarily, f does not necessarily have to satisfy either of these properties. So for example, following polynomial here, its Newton polytope is a square, which we can decompose as a vertical line and a horizontal line. However, because of the actual coefficients, right, if we have more information about the polynomial, we see that this can only ever factor as two smaller squares. In particular, it's a square of an irreducible that has a Newton polytope that is a square. So this would be only homothetically reducible polynomial. And the reason we care about this property is one can show through fairly standard arguments that if your dispersion polynomial or a facial polynomial, if your dispersion polynomial is only homothetically reducible, then your expanded dispersion polynomial, phi sub AB, or the corresponding face of phi sub AB are also only homothetically reducible. So this is why I showed that. I wanted to emphasize that since we have this linear map between the Newton polytope of phi and the Newton polytope of phi sub AB, the faces corresponds. Even though this isn't actually a face of phi sub AB, when I write restricted to F, I mean the face after taking that scaling, or, after that dilation map. So one of the things that Jory and I showed is that if all your facets, except possibly one, have only homothetically reducible facial polynomials, then F has to be only homothetically reducible. So now we don't, I guess the reason for using this is if we want to conclude F is only homothetically reducible, we really only have to look at the facial polynomials. As long as sufficiently many of them are only homothetically reducible, we can extend that to F itself. And only homothetic reducibility is very convenient for checking irreducibility, since all we need is a single facial polynomial to be irreducible. If we know that F is only homothetically reducible, to get that F is irreducible. Oh, yes, so go back. Uh-oh. Oh, that was all the way back here. Okay. So it's just the restriction of your monomial terms to the integer points that show up on that face. So, for example, our polynomial here, we're taking the dispersion polynomial, so we have minus lambda, technically over there, which gives us a lambda squared. Then we have minus x times -1 multiplied by the sign of our permutation to get this minus x, and minus y times -1 multiplied by the sign to get minus y. So your face polynomial is just only the integer points that show up on that face. You restrict to the terms that correspond to those integer points. You restrict to the terms of that polynomial that correspond to integer points that show up on that face. So in this statement, it's facets, but there is a more general way of stating this, just for the sake of not having to introduce extra notation definitions. It's like this, but I could talk to you more later about that. Sorry. Wait. Oops, that's the wrong slide. Okay, although it is the next slide. Any other questions about this? Okay. So we say that a face is potential independent if our facial polynomial is it does not depend on our choice of potential v. So an example of that is actually the facial polynomial we just went back to, lambda squared minus x minus y. No matter my choice of potential, the coefficients of that facial polynomial are not affected. It's the same polynomial regardless of my potential. And so one of the things me and Jordy showed, which has been slightly buffed by some recent work done with Liu, not the Liu I've been mentioning, but a different Liu, who's a graph theorist. If all the facets of the Newton polytope of your original dispersion polynomial, except the base, are potential independent, then the corresponding facial polynomials of phi are only homothetically reducible. Oh, sorry, and the corresponding facial polynomials of phi are only homothetically reducible. Then you know that phi sub AB is only homothetically reducible for all potentials. Moreover, I mentioned these results earlier about if we fix a Z2 periodic potential. Well, if my face is potential independent, then my facial polynomial of phi sub AB in this case is also potential independent, and which means this is also the facial polynomial for the zero potential. So that's a Z2 periodic potential. And so we can apply those same results that I had initially listed to the facial polynomials of phi. So let f be potential independent, and our facial polynomial is irreducible with some term x to the r, y to the s, lambda t, and we get the same thing. If a is coprime to both b and r, or b is coprime to both a and s, then phi sub b restricted to f is irreducible. And once again, if you have both x and y appear as terms in your facial polynomial, then no matter your choice of a and b, you always get the corresponding facial polynomial of phi sub b is irreducible. So let's go back to our right example. Here I have just set alpha, beta, gamma to 1. This is when you set all your edge weights to 1. This is usually referred to as a Schrödinger operator, which is also, I guess, an important subclass of operators, discrete operators. But we have the following dispersion polynomial for the original hexagonal lattice dispersion relation. We're viewing it as Z2 periodic, right? Just back to our right example. As I mentioned before, that one face is invariant with respect to our choice of potential, but one can show this actually is true for all of our facets with the exception of the base. But as the theorem stated, we don't have to worry about the base. Moreover, all these facets are triangles. These are pyramids, and therefore only homothetically reducible. So combining potential independence and only homothetic reducibility, we can use Jordan's theorem to obtain that phi sub ab is only homothetically reducible. Now, going back, since we have a polynomial that's only homothetically reducible, we just need that a single face now is irreducible to conclude our polynomial is irreducible. If you recall that example I was showing you, that was lambda squared minus x minus y. So this is a facial polynomial with both the terms x and y. Therefore, we can conclude that phi sub ab, that facial polynomial of phi sub ab is irreducible. So now we have that phi sub ab is only homothetically reducible. We have an irreducible facial polynomial. So we conclude that phi sub ab also must be irreducible. And since these are potential independent, no matter what I choose as my potential, it doesn't actually affect anything. So we're able to conclude that no matter our choice of a and b, phi sub ab is irreducible for any abz periodic potential. So we get something better than just generic potentials. We actually show it holds always, no matter your choice of potential. And yes, I have minutes. Okay, and I guess Joy and I use this not to just prove examples where things just end up being irreducible for block varieties, but we're also able to apply slight variations of our theorems to show that the block variety associated to the dice lattice is composed of a times b up to a times b flat bands. It could be irreducible, but if it does factor, it has a times b flat bands union with one irreducible hypersurface. Let me explain what a flat band is. Just think of a flat band as a flat band just corresponds to there being a linear factor in lambda of our original dispersion polynomial. So that's why they're called flat, because in the actual block variety, this corresponds to one of those sheets just being completely flat. And one of the reasons the spectral theorists care about flat bands is when this happens, you have a true eigenvalue in your spectrum, which, as I mentioned before, is believed to be a fairly rare thing. Usually, you only have a central spectrum when looking at the spectrum of your operator on the space of square soluble functions. And we were also able to apply some of the results that me and Frank came up with in Joy and I's paper to show that if you have a generically labeled dense graph, then there exist infinitely many choices of A and B, or A, B, and C, such that your block variety is irreducible for all potentials of those periods, of course. And moreover, we're able to get some results on Fermi varieties, specifically when you consider the Fermi varieties of a Z3 periodic dense graph. you can, once again, you don't know, so it's not as strong as for graphing where it doesn't actually matter our choice of A, B, and C. There might be some restrictions on A, B, and C, but you know for sure that there exist infinitely many combinations of A, B, and C such that you're able to conclude irreducibility for all potentials. All right. And that's all I have. Happy birthday, Frank. And,
Any questions for Matt?
yes.
The hypothesis on one of your main theorems is the existence of a monomial x to the r, y to the s, and lambda to t.
Yes.
So that, how a strong hypothesis is that? Because it sounds like you need to know about the support of the
yeah, so this is
polynomial.
very much tuned to the case of two dimensions. So what me and Joy did actually holds in any dimension. It's just, it's very ugly to state it in generality. So this is with restrictions to Z2. But basically what our results show is that there's kind of this trade-off between how much you know about the support and how many, I guess, like what you're left with for choices of A and B that allow you to obtain irreducibility. Basically your support provides some set of restrictions. So for example, if Thomas talked about lacunary polynomials. If your polynomial is lacunary, there are going to be some restrictions on your choice of A and B. Necessarily. Is that okay?
Any other questions? All right, let's thank Matt.